In the last section, we talked about Cartesian product of two sets. Recall that the Cartesian product of two sets is a set of all possible ordered pairs A comma B, whose first element A should come from the first set A, and the second element in the pair B should come from the set B. Now we will talk about function. Function is the most elementary tool in calculus and in analysis. Let's have a formal definition of function. Let A and B be two sets. A function f from A into B is a subset of the Cartesian product of A with B, with the property that for every x in A, there exists a y in B such that the pair x comma y is in the subset. And if there are two pairs x comma y and x comma z in F, then y must be equal to z. The set A is called the domain of the function f, and the set B is called the codomain of the function f. The following set of all y's in B such that x comma y is in the subset f for some x in A is called the range of A, often denoted by this symbol, range of f. So the range of a function contains only the outputs for some input. Observe that the range of a function f is a subset of the codomain. So the range of f is a subset of the codomain. They need not be equal always. If f is a function from a set A into B and the pair x comma y is in the subset f, then the element y in B is also denoted by this symbol, which is read y equals f of x, or f, the map, sends x to y. If f is a function from a set A to real numbers, then f is said to be a real valued function on A. Image and inverse image. Definition: let f be a function from a set A into B. If E is some subset of A, the domain, then f of E, it is called the image of E under F, is defined by this definition. So f of E is a set of f of x in B such that x is in E. Means f of E contains only the outputs in B whose input were in E. For example, if f is a function from a set A to the set B and E is some subset of A, and suppose the definition of f is the following: f at 1 is A, f at 3 is also A, f at 2 is B, f at 4 is D. We can also show this definition with the help of this ellipsis. So 1, 2, 3, 4. And we have A, B, C, and D. Suppose f is a function defined by this formula. F at 1 is A, f at 2 is B, f at 3 is A, f at 4 is D. Notice the element C in the codomain has no preimage in A. Means there exists no element in A whose image under F is C. This is okay by definition. So the image of E under F is the set A, B, because 1 has the image A, 2 has the image B, and 3 has the image A. So f of E contains all the images of the elements in E. If F is a subset of B, then the inverse image of F, denoted by F inverse of F, is defined by the following. So F inverse of F contains all the X in A such that whose output f of x is in F. For example, let f is a function from a set to another set, and f is a subset of the codomain. We may consider for the moment this is A and this is B. So f is some subset of the codomain. So we have the definition of f as follows. F at 1 is same as f at 3, which is equal to A, and f at 2 equals B, and f at 4 equals D. So the inverse image of f under f would be 1, 2, 3, because the inverse image of A is 1 and 3, and the inverse image of C is empty, and the inverse image of B is 2. So the inverse image of the complete set F ABC is the set 1, 2, 3. Now we observe that if we apply F to this set to consider the image of this set, we obtained A comma B, which is not exactly same as F, but instead a proper subset of F. Similarly, if E is some subset of A, then the inverse image of the set F of E is a subset of E. The equality need not hold. In either cases. In particular, if Y is an element in B and F is a set containing Y only, then for convenience, we will use this symbol instead of this. So this is the F inverse of F, but since the set F contains only a single element, Y, so instead of putting so many braces, we will write F inverse of Y. So by definition, F inverse of Y is a set of all X in A such that whose image equals Y. For example, F is a function from set to another set, and E is some subset of the codomain, just like before. then we can calculate the inverse image of A under F. The set of all elements in A, the domain, whose output under F gives us A. And we see, by definition, the elements are only 1 and 3, because F at 1 is A and F at 3 is also A. We also observe that F inverse is by definition not a function. It is just a symbol used for the inverse image of the set containing A only under F. Proposition: if F is a function from A into B and A1 is some subset of A2, a subset of A, then the image of A1 under F is also a subset of the image of A2 under F. To prove that, pick an element Y in the set F of A1. Then, by definition, the inverse image of Y under F must be a subset of A1. Since A1 is a subset of A2 and F inverse Y is a subset of A1, which is a subset of A2 by the hypothesis, so F inverse Y must be also a subset of A2. This means that Y must be in F of A2. Therefore, F of A1 is a subset of F of A2. Because every element Y in F of A is also the element of F of A2. This concludes the proof. Another proposition: let F be a function from A to B, and B1 is some subset of B2, subset of B, then the inverse image of B1 under F would be a subset of the inverse image of B2 under F. That simply means we can memorize this way. We can apply the inverse of F to both sides of this relation. Please try to prove it. Theorem: let F be a function from a set A into B if A1 and A2 are subsets of A, then the following statements hold true. F of A1 union A2 equal to F of A1 union F of A2. So we can simply distribute F over the sets A1 and A2 over the union. But the second statement says F of A1 intersection A2 is a subset of F of A1 intersection A2, F of A2. The equality need not hold in the second statement. Let's try to prove this. So we pick an Y from this set F of A1 union A2. Then by definition, the inverse image of Y under F must be a subset of the set A1 union A2. This implies that the inverse image of Y under F must be a subset of A1, or F inverse Y is a subset of A2. This means that Y must be in F of A1 or Y must be in F of A2. So combining the or, Y is an element of this set F of A1 union F of A2. This shows that the set F of A1 union A2 is a subset of F of A1 union F of A2. In a similar fashion, we can also show that the set F of A1 union F of A2 also a subset of F of A1 union A2, just by following the steps in backwards. This concludes the proof of A. You can try to prove the statement B. Suppose someone presented a proof by following the steps in the first part of the proof in the backwards to prove that F of A1 intersection F of A2 is a subset of F of A1 intersection A2. These are the steps that he or she produced. But this is false. Can you identify the false step in this proof? Please pause the video and read the proof and try to identify the step that went wrong. If F be a function from a set A into B, and B1 and B2 are subsets of the codomain, then the following statements hold true. Please try to prove these statements following the definition of the inverse image of F.